Hey there, my name is Alejandro, and welcome back for day 101 of me doing the NeetCode 150 challenge. So today we're doing another LeetCode Medium 1D dynamic programming problem, and without further ado, let's get straight into it. Okay, today we got LeetCode Medium problem 300 longest increasing subsequence, and seems like we've solved this problem before. Not only that, we have something in here. Let's make sure that we reset that because I don't want to see anything that's in there. Since it seems like we've done this problem before. When was the last time? Ooh, we got wrong answers last time. Last time we did it was June 4th, 2024. And here I kept getting wrong answers. Interesting. July 30th was during the daily LeetCode challenge. Oh, maybe I was doing this problem and so on. Okay, interesting. Okay, so given an integer array nums, return the length of the longest strictly increasing subsequence. Okay, okay. This problem is I think I don't know if I don't know if it's my first ever introduction to dynamic programming. It was no, okay. So my first ever introduction to dynamic programming was with Fibonacci numbers with Eric Domain on MIT OpenCourseware lectures that are free on YouTube. But yeah, this is the very first time I got introduced to dynamic programming at the University of Toronto, Scarborough. It's just that I happened to watch that DP lecture before I took my advanced algorithms class. But yeah, this was the very first problem we learned how to do at the University of Toronto, Scarborough, right? And the way that this algorithm, like I already know, obviously it's the very first problem we do there. The idea is essentially 1D dynamic programming, but inside of the body you'll do O of n work, so it's an overall O of n squared algorithm, right? I think even Eric Domain, in one of his problems, he goes over this one specifically. It's just not the very first one that he covers because he thinks like I guess something like a Fibonacci is probably easier to get a student into, right? Which totally agree. At least for understanding how DP works, right? And so, but this is a very great problem, a very classical problem. And if I actually understand correctly, I think there's actually an O of n log n way to solve this problem. That's what Eric Domain said, I believe. I think I remember looking that up one time. There was like some binary search way of doing this problem, which I actually don't know how to do because I didn't read too carefully into the algorithm. Just because like when I think of this problem, I think of the DP way, anyways, right? And here's like one of the 1D DP problems to do instead of the NeetCode 150. Pretty much like almost every university, like when they cover dynamic programming, will go over this problem. It's such a famous DP problem, and just one that's nice in terms of like understanding what DP is all about, right? And so the idea here is essentially we're gonna find the length of the longest increasing subsequence. Probably we'll do starting from we can do ending at an index I, we can do starting at an index I. The point is that we'll need to go like look at every single other thing from there and so on, blah blah blah, right? We could do the longest increasing subsequence that starts at an index I, maybe. That way, essentially, it's like, out of every single index I that's bigger than us, we'll do 1 plus that guy if it happens. Yeah. So, okay, yeah. We can do... Yeah, I like starts at an index I a bit more. Right? So here we'll do def dp of self comma I. Here we'll say def, this will be dp of I is equal to length of lis that starts at index I in nums, right? Right? Because here it's subsequence, right? And subsequence, so DP is really good whenever you have to do subset or subsequence and so on. It's amazing for those types of problems, right? That's why this is such a classical one. Essentially here, in terms of solving the original problem, like, we have if we have DP of I as, the length of the longest increasing subsequence that starts at an index I, then here we can just say, like, return max of, is length of nums at least 1? Yeah, it is at least 1. So here we'll say max of self.dp of index I for I in range length of nums, right? And there we go. Bada bing, bada boom. There we have it, right? And so here we'll do self.memo is equal to this, as well as self.nums is equal to nums, obviously. And here we'll say if I in self.memo return self.memo of I. If I is greater or equal to length of self.nums, then here we'll return 0, right? There is no more subsequence that you can do from there. Otherwise, it's like we're starting at index I, right? We are starting the longest increasing subsequence at index I. So and yeah, it must be strictly increasing subsequence. So the idea is that we fix the value at index I, and then it's like, for every single larger value that happens after us, we can consider like the longest increasing subsequence from that value plus 1, because we're doing it from an index I plus that 1 and so on. That's kind of the point, right? Index I. So here we'll say start val is equal to self.nums at index I, right? Then we'll say for j in range I plus 1 all the way up to length of self.nums, then we'll say, here we'll do nums is equal to self.nums. If length of nums greater than, here we'll just do nums. We'll just do nums. Here we'll say, what will we say? Yeah, if nums of j, it must be greater, right? So if it's the case that this is larger than nums of I, or a better way maybe it's like, if nums of I is strictly less than nums of j, then we can essentially attach the longest increasing subsequence starting from index j on top of the right after this I, right? So here we could say res equals length starting at index I. Base case, only take number at index I. Okay, here we'll say if res is less than, here we'll just say res is equal to max of res and 1 plus self.dp at index j. Here we'll say self.memo of I is equal to res, return res, right? So something like this I would expect to work, and let's see if it does. Okay, it does, accepted, let's submit. Yeah, a little bit slow, but there we go. And so yeah, 7% solution. So okay, people are doing it faster. And yeah, okay, this is like, the supreme hackers and so on. So yeah, I am aware that there is an n log n way of doing this problem, because Eric Dermain did say that in one of his dynamic programming lectures as like a little fun fact, like, oh, by the way, there's an n log n way of solving this problem and so on, in case you're curious and so on, but it's not DP, and then there you go, right? So I won't bother with that, but yeah, it makes sense to see a little spike like this over here. Okay. So yeah, so here we can maybe do some O1 optimizations. Let me think. New case is equal to 1 plus self.dp of j if new case larger than res equals new case, right? Or if res less than new case. There we go. Yeah, so now we're close to the standard deviation. So yeah, so okay, so it's just gonna be like, modifying the O of 1 stuff, right? Yeah, so it's like instead of using max, just do that. So yeah, it's just O of 1 stuff here. So yeah, so we're at the standard deviation curve over here, where I'm guessing is like, all the DP solution folks, and this is probably all the n log n solution folks. So it makes a lot of sense. What is the size? Yeah, so 2500 squared is so 25 is 5 times 5 times 100, and so squared. Yeah, okay. Let's just do Python 3 2500 to the power of 2. Is, yeah, what's 10 to the power of 6? So yeah, so this is like 6 times 10 to the power of 6 and so yeah, it's like a big list. So yeah, something like n log n will definitely make a huge difference. So yeah, so this is probably the guys that found an n log n solution, which I am aware of is indeed something that exists, but I also know that it involves binary search and it's not a dynamic programming solution, so I do not feel too guilty. Oh yeah, follow up. Can you come up with an algorithm that runs in O of n log n time complexity? Okay, so I know it involves binary search. I don't know how you would do it, right? In terms of the NeetCode 150 challenge, like, we did solve this problem in terms of the NeetCode 150 challenge, just because it's like, this is meant as a 1D dynamic programming problem, right? And I've never actually bothered how to come up with the n log n solution time. So yeah, so it seems like it's an actual follow-up to this thing. And I do know that it involves binary search, right? Where it's like, okay, maybe it's like, yeah. Yeah, okay. Maybe I can like, research that in my own time. But in terms of actually, solving the problem in terms of the NeetCode 150 challenge, we did it, right? We wanted, finding a 1D dynamic programming solution. This is a very, very classical 1D DP type of problem, and we did exactly that, right? So like, index, and like, I know this is like, the expected solution because like, this is literally what we go over inside of college, right? This very first problem that we solve at the University of Toronto Scarborough for dynamic programming is this exact one, longest increasing subsequence, O of n work in the body, O of n total subproblems. This is O of n squared time, right? So here this is time complexity, T. So this is O of n subproblems, O of n time per subproblem equals of n squared total time. There we go. Nice. Okay, so we can submit this just one more time. And there we go, bada bing, bada boom. So yeah, so we're at 18%, but we're like, right in the middle of the standard deviation curve over here, which tells me everything I need to know. It's just like, we are at the optimal point in terms of the people that solve this in the dynamic programming way. So there we go, bada bing, bada boom. Okay, so as always, in all my videos, I do a quick recap of how I always solve this problem. So this one essentially, we want the longest increasing subsequence. So what does that mean? Essentially, it's like pick a subset of the numbers, not a subarray, a subset or subsequence of the numbers, such that, well, obviously it needs to be a subsequence, so it needs to be like, from left to right, right? But it's like the point is that you can skip numbers, right? So it's like, I can pick my 10, then I can like skip the 9, and then pick my 2, skip the 5, skip the 3, pick a 7, skip the 101, skip the 18, right? So the point is I can grab any subsequence that I want, right? And I need that subsequence to be strictly increasing, right? So if I pick this 10, I can only consider numbers that are larger than 10. So I can't consider 9, I can't consider 2, I can't consider these, but I can consider 101, right? Or I can, if I consider 101, then I can no longer consider 18 because it's not bigger than 101, right? But if I don't consider this one, then I can indeed consider 18 because it's bigger than 10, right? And so essentially we want the longest increasing subsequence inside of the entire array. And so the way that I did this is like, okay, how about we solve the problem, which is the longest increasing subsequence starting at index I, right? So longest, I'll just abbreviate longest increasing subsequence to LIS. So here, the LIS starting from index 0 over here, the LIS starting from this index, 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 oh, and so on and so on. And so what do we want to return? If we know how to find the longest increasing subsequence that starts at an index I, return the longest increasing subsequence that starts at an index I for every single I in the range of the array, right? Because the longest increasing subsequence, wherever it is, must start at some index I, right? So if you find the longest increasing subsequence for every single index I and then take the max of those, then there you have it. You have the longest increasing subsequence overall, right? So that's essentially what I do. So the dp of I returns the length of the LIS that starts at index I in nums, and we just return, max of delta dp of I for every single I in range of the length of nums, right? So hopefully that makes sense. Otherwise, let's look over how we do this. So as always, like, if I is in self.memo, return self.memo of I. So if we've computed the result before then and it's in our cache, then return the value from our cache. No need to recompute. Otherwise, it's like, okay, nums is equal to self.nums, just defined up here. So if I is greater or equal to the length of nums, then we return 0, right? So at some point, like if we reach the end of the array, there's no more elements for us to pick inside of our subsequence, so 0 more elements, so we return 0, right? Otherwise, it's like, okay, we want the longest increasing subsequence that starts at index I, right? So for example, here if we're 0, so we want the LIS that starts at index 10, no matter what. Well, this is going to be the very first value. Since we want everything to be strictly increasing, right? That means that every single number after the index 0 number, which is 10 here, must be greater than me and strictly larger than me. So I can only consider numbers that are strictly greater than 10 from so on, right? And the way that I do it is very naive, right? Essentially what I'm going to do is essentially loop through every single one of the indices after the current index that I am, right? So if I'm at index I, I'm going to go from index I plus 1 all the way up to the length of the numbers. And for each one, I'm going to ask myself, right? So if I'm at this index initially, I'm going to look at this number and be like, is it greater than 10, right? In this case, it's not, so I skip. Is this greater than 10? No, I skip, right? So if nums I is less than nums j, right? So is 10 less than 2? No, it's not. Is 10 less than 5? No, it's not. Is it less than 3? No, it's not. Is it less than 7? No, it's not. Is it less than 1 and 1? Yes, it is, right? So what do I do? It's like, okay, for every single number that comes after, like, you know, this 10, for example, I'm going to look at each and every single one. And if that number is bigger than 10, like this one, then what I'm going to say is I'm going to grab the longest increasing subsequence that starts at this guy, right? And then once I get the longest increasing subsequence that starts at this index, then I'll do 1 plus that value, right? Because it'll be 10 is the very first number, then 101 I can have as my second number, so I'll just do the longest increasing subsequence that starts from 101 and onwards, right? And that's kind of the idea, right? Or I can do 10 and the longest increasing subsequence that starts from 18, and then all that plus 1, right? Because it's like longest increasing subsequence that starts from 18. In this case, it's just 1, it's just 18 and so on. But then it's like plus 1 because it's like 10 to 18, and then the longest increasing subsequence from 18 and onwards, right? So here I loop through every single index j that is starting from index I plus 1 all the way up to the length of nums. And then I ask myself, okay, if you know the index I number is less than the index j number, then I can have, like, you know, the number at index j as the second number in my subsequence, where the first number is the one that starts at index I, because again, we must start the longest increasing subsequence at index I, because that's the way we define our dp of I function. And so then we'll say, okay, it'll just be 1 plus the longest increasing subsequence from the number at index j, right? We go from the number at index I, the next number will be the one at index j, and so the rest of the longest possible increasing subsequence that we can get will be the longest increasing possible subsequence that we can get from index j, right? And so so here, like, the new case will be 1 plus the longest increasing subsequence from index j. And if, you know, here we have result, which is initially 1, because obviously, like, you know, starting from index I, you can have just the number at index I, and then you have, you know, an increasing subsequence of length exactly 1, so you can always have a length of exactly 1. And also because, like, you know, numbers is at least 1 in length, so, like, you know, the minimum value of a return is 1, so we just initialize res to 1. And we say, okay, if res is less than that new case, then update res to that new case, right? So essentially, res is always the max out of every single possible we can see, right? So for every single number after index I plus 1, right, or every single index after index I, we'll say, okay, if the number at that index is bigger than the number at index I, then we can consider that guy as the second number in the longest increasing subsequence, and then it's like, it'll be just 1 to get to the second number, and then the longest increasing subsequence from that second number onwards to essentially encapsulate the full length of the longest increasing subsequence starting from index I, right? And we'll do that for every single possible index j from index I plus 1 and onwards, right? So that's kind of the point. And at the end, once we compute a res, we just cache that result in case we ever need it again, and then we return res, and there we go, bada bing, bada boom. And in terms of the time complexity for this problem, it's for each index I, so there's at most, like, you know, length of nums possible problems, and then for each one we do, like, you know, an O of n loop here. So this is O of n work per subproblem, so it's like O of n subproblems, O of n time per subproblem, so O of n squared total time, right? And that's essentially it in terms of how I was able to solve this problem. So yeah, so hopefully that just made sense. And otherwise, that's pretty much it for this video. If you did find it useful or enjoyable in any way, shape, or form, I would highly appreciate it if you left a like or comment. But otherwise, I'll catch you in the next one. So until then, ciao, ciao, my friend. Bye-bye.